All right, there's one more thing we can do. We have not yet, we're actually technically done, but just to make sure that we haven't made a mistake, I'm going to look at all the forces acting on this 5 kilogram object and see if we get the same answer. We should be able to get tension to be this 20. So I'm going to clean up just a little bit of this, just to give me a smidge of running room. That's probably all I need. And now the free body diagram looks a little different. We no longer have this 52 Newton working on it, and it still has a gravitational down and a normal force up, which their amounts would be different on this one, but we're going to ignore those anyway because they travel up and down, and that's boring to me because they add up to 0. So here is the free body diagram for the 5 kilogram object. Now, just working with this, that means that the formula is now just T. The sum of the horizontal forces acting on the 5 kilogram is just T. You'll notice it's a positive number now because it's pointed in the positive direction. And then I replace this 8 with 5 kilograms, the mass of the object we're looking at. And 5 times 4 is 20. And so we get 20 newtons again, which is good. You notice I didn't have to change that. That's because you're looking at a Newton's pair. The right end of this string has a certain tension, as does the left end. That means it passes the 4 necessary litmus tests to be a Newton's pair. There has to be 2 of them. They have to have the same magnitude, in our case 20 newtons. They have to point in different directions. That happened. And they have to happen on 2 different objects. So, again, you don't have to do that, but it's good if you would like to check your work, make sure you haven't made a math error. All right, let's find this a somewhat harder one. How would it change things if we change the direction that the external force is being applied? We can turn the external force around. It's still 52 newtons. It's now pushing on these 2 boxes, and because it's pushing, I went ahead and took the string out of the way. Now, there will be a lot of similarities. When we add up the masses, we still get 13 kilograms. We still have an external force of 52 newtons, so when we apply it to Newton's second law, we're still going to get that the acceleration is 4. But now, because the external force is pushing in a different direction, it's pushing rather than pulling, actually, motion is going to be from right to left on the page. So we still have a positive acceleration, but we've just defined positive as the direction to the left. Well, what else does that change? Well, let's look at the free body diagram for this 8 kilogram deal. It's going to be similar to this, but not identical. All right, so this is the free body diagram. There, I cleaned it up a little bit. 52 newtons pushing to the left. That's the external force. And to the right, well, it says tension, but we can't really call that tension anymore because tension is a word we reserve for one-dimensional forces, strings and such. So I'm going to call that the force, what do I call it? Force of 5 on 8. That's the 5 kilogram box on the 8 kilogram box. That's maybe a bad way to name them, but I think you get what I mean. Box 5 is exerting a force on box 8 because box 8 is trying to push past it, and that can't happen. So now again we are already down to step 4. Draw the free body diagram for each object. We've done that for the 8 kilogram. Apply Newton's second and or third law. Well, here's Newton's second law, that line. When we will get rid of these, remember that was 20 newtons because we're going to need that in just a minute. But wait a second, I've just broke something. Let me fix it. So the sum of the forces, again horizontally, on object 8 kilogram is 52 newtons. 52 is a positive number because the push is from right to left, the acceleration is from right to left, and therefore from right to left is considered positive. 52 newtons minus the force of 5 on 8, so all the forces acting horizontally, that is going to make, that's the sum of the forces, that is going to make the mass have a certain acceleration. The mass in question, the one we're looking at, is the 8 kilogram, and the acceleration is 4 meters per second squared. And for reasons that befuddle me, those are all capitalized, probably because I got caps lock on. Well, see, there you go. And so that is 32 newtons. And if we were to simplify it, which I reckon we will, we would get that the force of 5 on 8, sorry if y'all have to see this happen, is 20 newtons, just as we expected. I won't bother doing it, but if we looked at the 5 kilogram, the only force it would have would be a force in this other direction, a force from box 8. That would be this. Actually, I said I won't do it, but let me do most of it. The forces on it, I'm going to fix my issues here. That's not a force, and this is, but it's typically not that long. It would look like this. This is for object 5 kilogram, and it has a force of 8 pushing on it. That's the only force there. All right, so we have here force of 8 on 5 is 5 kilograms, again the mass of the object we're looking at, times the acceleration of the system, 4 meters per second squared, and that's going to total 20 newtons, which we expected. Oops, need to fix this. There we go. And again, that's a Newton pair, so doing it that way changes almost nothing, and that's as it should be. All right, let's really complicate it now. All right, here's a somewhat more complicated one. I've got 3 masses now, and I've labeled them object number 1, 2, and 3, and they have 5 kilograms, and 20 kilograms respectively, and they've got an external force of 90 newtons. I've taken all the other clutter away. If you need those steps, I hope you wrote them down, or you can back the video up and write them down now. But step 1 is you simplify the situation. You treat all of the masses as one. Said another way, you just look at the entire system. So I'm going to draw a free body diagram for the entire system, and it looks like this. We've got a normal, or gravity pulling it down because it has some mass, a normal force pushing it back up. We know enough to where we can calculate those, but since they add up to 0, it's boring, so we're going to ignore them, and we're just going to look at the horizontal forces. Here we have this external force of 90 newtons. There are some internal forces between each box, but that's only there because the 90 newton is causing it to be there. So we can right now ignore them. So what do we have? We have a total external force of 90 newtons and a total mass of 30 kilograms. And that looks like it calls for Newton's law. There's Newton's third law. And when we plug the particulars in, 90 newtons is the only force we have acting horizontally, is equal to the total mass, 30 kilograms, times some unknown constant. That is, we don't know the value of the acceleration, but we can do the math, probably in our head, and find out that the acceleration is 3 meters per second squared. That's the entire system. Now we have to go back and look at each individual component. We could start from any end. I'm going to start from the left end, because it only has one force acting on it. The only force acting on it is box number 2 pushing on it. So the free body diagram would look fairly similar to this, except that instead of this 90, I've got to come up with some subscript that describes the interaction between these boxes. So I'm going to call it F of 2 on 1. Hope that doesn't confuse you, but that's box 2 pushing on box 1. That's the only thing that's making box 1 move. Now, according to Newton, let's do this. I'm going to put this right here. According to Newton, you sum up the forces. So now we have the sum of the forces would be this unknown value F F2 on 1. And it's going to make this mass, which happens to be 5 kilograms, have the acceleration that we, a moment ago, decided the system had, that being 3 meters per second squared. When I work that out, it's 15 newtons. So the force of F2 on 1 is 15 newtons. I'm going to write that down in a convenient place. There we are. Now and that's all there is to object number 1. Now let's look at object number 2. Well, it's a little different. It actually has 2 horizontal forces acting on. There we have it, where we can keep track of it. Now we're done, or if you'd like, we could verify that the force of 2 on 3 is 30 newtons. I could do that here, but I'm going to leave it for you to do because I think it's straightforward enough now to where you know how to do these on your own.